value. Now you increase it further. Now calculate that theta is equal to 0.05 radian. What will be the value of M1? Into? Yeah, 4, sorry. Not 2, 4. You are right. So that is now at theta is equal to 0.05. What is the value of M1? 100. M2 is also 100. So Q will be and how much is delta? Okay, so if I plot Q versus delta at 35 mm, sorry, not 35, at 80 mm, this is 35 kilonewton, and at 250 kilonewton. Okay, and then it will continue till when? Both go up to 0.05 radian. So 0.05 radian, this will be delta U. Delta U will be sorry, I have just 1 0 here. Delta U will be 0.05 into Q. Okay. Yes. This is a common mistake you have made in the tutorial also. If these beams, left and right beams, are not same, then the reaction here and here is not going to be same, because there is a reaction here. So if you are calculating that reaction, do not forget this reaction, because compatibility is to be maintained. So at same compatibility means same rotation. Same rotation, there are different moments. If moments are different, how can the reactions be same? Reactions will be different. And if these reactions are different, to balance in the vertical direction, a net reaction will act here. Yes? You can do by many approaches. But answer will be. So if you are not getting this answer, whatever approach you have used, look into where you have made a mistake. Somewhere you have made a mistake. The answer is not there. You can use any approach. If you have not made any error, finally the answer will be. Okay, you can calculate EI if you are very fond of calculating EI. You can calculate EI from angle over theta. Calculate EI and then you can do if you want to do that. I have simplified it so that you don't need any calculation, but I have thought that the simplification will be heavier on you. I have never imagined that I am doing something to make your life simpler and it will create more problems. Now the second question. This is our side. This is 30 kilometers, 20 kilometers. This is 30 kilometers and this is 20 kilometers. And we have one fault here and another fault here. This is fault 1, this is fault 2. Yes, anything you have to discuss question number 1, first ask me. Let's finish that. That will move to question number 2. But first be satisfied with this. Any angle, any direction, any point you want to discuss, ask.
Yeah, that equal reaction taking
Equal?
considering symmetry, we have to consider
There is not symmetry. It is not symmetric. Because why it is not symmetric? Because moment rotation curves are different for left side beam and right side beam. So it is not symmetric. You can't consider symmetry.
The symmetry we are considering is going means whatever symmetry we are considering till now is based on reflected shape and not based on capacity.
So the reflected shape is not same. For one beam, if you are applying, let us say you are applying same moment, one beam is going to reflect more, another beam is going to reflect less. But if you are applying same reflected shape, okay, same rotation, then one beam will generate less moment, another beam will generate more moment. So where is the symmetry? There is no symmetry.
That is generating different moments is okay, but deflected shape is same for particular theta rotation. Means theta A, theta B equal and deflected shape is same for that. And for that,
that is not symmetry. Deflection, same deflection on left and right doesn't mean that these will be symmetric. Deflection in left and right will be same in any case. Whatever you do, compatibility is to be satisfied.
yes,
So whether it is symmetric structure or not, the rotation from left side and right side is going to be the same. Just rotation being same doesn't mean that it is symmetric. The structures also have to be mirror image of each other. This is not mirror image.
But whatever assembly we have made from the big structures was all that are based on the only deflected shape, not on the capacity.
Symmetry is not just based on the rotation. The whole structure has to be same. EI also has to be same. For example, the simplest case we considered this. Okay. This reflected shape is like this.
Yes.
Suppose I change the stiffness of this. It will not be symmetric. So, the structure also has to be mirror image and then deflected image will be mirror. Deflected shape will be mirror. So, just because here theta is same, suppose I have this, even then the theta here going to be the same. But that doesn't mean it is symmetric. So the problem is that this particular problem is not symmetric, and you might have used symmetric. So that's why for symmetric you have to be clear that in which case it is symmetric, in which case it is not symmetric. So it is not symmetric. Any other problem?
What the steps we have followed till now? If we did that, and at last, while taking the ductility, I have considered the ductility of the beam which has low ductility, that is beam 1. It is coming 10, and for beam 2 it is coming 25. So I have considered the ductility 10 for taking delta U. So what is the wrong in that one?
See, you have to consider that beam which is reaching its ultimate displacement first.
Yes.
So which one will reach ultimate displacement
That
first?
beam 1.
Beam 1.
Yes.
Why?
Because ductility ratio is less.
But it is yielding also earlier. So ductility ratio is theta u by theta y.
Yes.
So suppose ductility ratio for one beam is larger,
Yes.
but its theta y is also smaller. So what will happen to theta u? So theta u in both the cases is same actually. So actually both the beams, if you calculate delta u will come out to be the same for both the beams. So you calculate for any beam, doesn't matter. Answer will be same. So if you have considered any one beam and you have considered it correctly, then also the answer will be same. In this case, not in all the cases, in this case, because here theta u is same, so delta u will also be same for both of them.
So,
Yes.
you said the reaction should be different at this support and this.
Right.
So, why reaction should be different?
Because the moment is different. This moment is different than this moment. That you agree? And equilibrium has to be satisfied for this beam. I have a beam where this moment is applied. So what will be the for the equilibrium? This moment, whatever moment I am having, counterbalance that I will have a reaction. If this length is L, so R will be M2 by L. Here in this case, this is M1, okay, and this is reaction R1. So R1 will be M1 by L. M1 and M2 are different. If L was different, then also reaction would have been different. Like in this case also, it will be different. Even if M1 and M2 are same.
But sir, that M1 and M2 are not applied one now. They are applied due to class Q was acting on that. These are the internal forces which act.
But internal forces have to be equal to external
But
forces.
the internal forces do not contribute to the reaction.
Why not? How does the reaction develop?
Acting.
Let's take a simple question. What is the internal force here in the beam?
This reaction
Which is W. W by 2. Here. So from here to here, how you are getting the reaction? Through internal forces only. Otherwise, how this force will jump here to here? So why you have this misconception that internal forces will not have reaction? Reactions will develop because of internal forces only.
But sir, if I change the capacity of that beam, that doesn't mean that the reaction will change. If I change the capacity of the beam that is lowered it down, then it doesn't mean that reaction will change corresponding to that capacity.
So reaction is not changing because of the capacity.
Ah.
Reaction is changing because of different EI. Suppose in this case it will not happen. Let us take this case. So reaction is not going to be the same.
Yes.
So here is what is happening. The EI of this is 100 divided by 0.05.
Yes.
EI of this is 100 divided by 0.002. So EI is different. So because the EI of these two peaks is different, EI of this beam is 100 divided by 0.02. So that should become 5 into 10 to the power 4 Newton. EI is also kilonewton meter, same unit. Kilonewton. Okay, radian is per meter. So it will be yes. Huh? You are right. Yes. So but m theta will depend on m phi. So because m theta is different. Okay. So EI is different. We can't calculate from here. We will need plastic length. Not worth discussing. Everything is worth discussing. Maybe you have made a mistake now. He will make that mistake in the final exam. So if you discuss that now, it will save him from that mistake. So whatever is in your mind, ask it now.
Everything is clear, but clear the one to symmetry. When to consider symmetry or consider.
When the structure, loading and deformed shape all are mirror image. This case we considered as symmetry. So the structure, loading, boundary conditions and deflected shape. In fact, when the structure, loading and boundary conditions will be mirror image, deflected shape will also be mirror image. Okay. So all these have to be mirror image. Then it is symmetry. If anything you change, you just change the support. It won't be symmetry. It's no more symmetry. You change moment of inertia. You make this 2i and this I. It won't be symmetry. You add one more load here. It won't be symmetry. Okay. So symmetry is here when everything is mirror. Not one condition. Okay. Any other point in your mind? वो जो आप लोग डिस्कस कर रहे थे पूछो what we were discussing. हाँ 8m I changed it. I corrected it. I had missed 1 0. So I have changed. So 1 0 I have missed. Any other point? So let's go to question number 2. So for fault 1, let us calculate the length L1 30 km, distance R1 from the site. The shortest distance is perpendicular distance here, that is 50 km. Then you can calculate magnitude M1 using the formula for reverse, all faults are reverse, put the value of L, okay, we will get M1 how much? 6.8. If you know this, you can calculate the PHA in G for fault 1 by putting that value of M and R in this expression. How much? 0.07. Okay, let's do this for fault 2. Fault 2, the length is distance is shorter distance is 30 kilometers perpendicular, but there is no fault here. Shorter distance is this. Shorter distance to the fault. If your fault was going like this, then this can be the shortest distance. But fault has stopped here itself. So shortest distance is not that. Okay, so you can calculate PHA G2 also. First calculate M2 and then substituting that value of M2 calculate PHA 2.11. Okay, then you can plot response spectrum SA versus T using the shape of IS 1893. So shape of IS 1893 is this is 1, this is 2.5, this is 0.4, this is 1 upon T up to 4 seconds, and then it is constant up to 6 seconds. Okay, so at 4 seconds from 1 upon 2, how much will be this value? 0.25. This multiplied by 0.11 G. That is SA in meter per second. You have to convert this into SD versus T. So initially, up to this it is cubic parabola up to 0.1 second. The value at 0.1 second SA is 2.5 into 0.11 into 9.81 meter per second square. So SD will be SA into 0.1 square divided by 4 pi. How much is that? 2.5 into 0.1 into 9.81 into 0.1 square divided by 4 pi square. 0.002. Then beyond that, it will be parabola up to 0.4 seconds. So at 0.4 second, SA is equal to 2.5 into 0.11 into 9.81. And SD will be SA into 0.4 square divided by 4 pi square. Actually it will be 16 times of this. So 0.032. That it will be linear up to 4 seconds. So at t equal to 4 seconds, SA is 0.25 into 0.11. We have obtained, yes, 0.11 into 9.81. How much is that?
Point 27.
And SD will be 0.27 into 4 square divided by 4 pi square. 0.1 meter. So this will be 0.1 meter. Beyond that, it is constant. So this will be parabolic. And at 6 seconds, at t is equal to 6 seconds, SA will remain same. So that will be 0.27 meter per second square. Okay, but SD will be 0.27 into 6 square divided by 4 pi. 0.25. So that's what plus mean of what? That will not mean. Mean is, why I am giving mean? Because you will look for sigma level. So mean and mean plus sigma. So mean value is not mean of all the sources. Mean is mean of the attenuation relation. Attenuation relationship itself gives you, for one source, it gives you mean and sigma. Okay. This attenuation relationship, it is a simple attenuation relationship, it does not give you sigma. It gives you only mean. That's why I have written mean. And which we will be using for analysis. Mean doesn't mean that I have hundreds of sources, so I will take mean. Otherwise, I will go on increasing the area. Okay. In place of 300 kilometer, I take a radius of 1000 kilometer. So many small earthquakes will come whose PGA will be very small there. So mean will be on reducing. So mean doesn't mean that we have to take average of all the sources. It is mean PGA obtained from the governing source. Okay, any other doubt? What is?
While selecting PHA, like we have to calculate for photon source and
Right.
equal to 12, that is 0.11 and something 0.0 something. So, like we need of to which one we have selected?
Whichever is that, we have, while writing the steps, if you look at the notes, we have written the steps. So here we have written that first we will calculate PGA from all the sources, and whichever source is giving us larger PGA, largest PGA, that is our governing earthquake, and we will design for the governing earthquake. You are simply multiplying this by h. For any, for converting theta to h for any mean, you have to multiply it by 4. So you are multiplying these by 4, you are multiplying these by 4, so your calculations are alright. Finally, this will also be 2, this will also be 2. So, at what value of delta this is giving? Delta, this is giving 2.02 mm. This is using at 2 mm. Now calculate the difference of these two. Theta p 0.25 by 0.25 and 2.5 by 4. And add 2 mm. You will get 180 mm. 180. This is 2 mm. 0.05 minus 0.005. 180. This is 180. 180 plus 20. Okay. Any more questions regarding the quiz? Yes, ma'am. Right. PHA value is actually Z. PHA is nothing but Z. So PHA, EPGA, this value is Z, which we call zone factor. Same value is EPGA. Same value is also called ZPA, and in attenuation relationship, this is called PHA. So all the names refer to this value. Any other doubt? Okay, so let's go back to what we were discussing in our class. So please come out of the quiz now, or tell me we will go back to the quiz. It should not happen that I am discussing something else and you are discussing something else. I am telling you to do it. क्या डिस्कशन चल रहा है बताओ हाँ वो तो हम लोग डिस्कस करने जा रहे हैं ना यू आस्क व्हाटएवर so we should all discuss when we are in the class. When you are outside the class, you can make any group and discuss anything, but in the class we can discuss anything, but whole of the class should discuss the same one. That's only thing I want. Okay, so we discussed how the inelastic system responds during earthquake. Okay, and we discussed 3 methods so far to calculate the roof displacement of a multi-story building when subjected to a given earthquake. What are those 3 methods which we discussed? First we discussed ATC 40 method. Then we discussed Equivalent linearization. In fact, ATC method is also equivalent linearization method. That is one of the equivalent linearization methods. Then we discussed displacement modification, DML. One more method I will tell you, that is based on what we call constant ductility response spectrum. So, same earthquake, first we had seen the response under elastic conditions. Then for the same earthquake, if I am using an inelastic second degree freedom system, then the response will be like this. Now what I can do is, I can design my structure for different yield strength. So if I consider different yield strength, so F5R, this F5R is the ratio of the yield strength to the elastic demand. Okay, so if the structure has to remain elastic, then how much force will develop? But I do not design for that, I design for reduced force. Ratio of the design force or the yield force to the elastic force is F5R. So when F5R is equal to 1, that means it is elastic. When F5R is equal to 0.5, it means that I have designed it only for half, or in other words, the response reduction factor is 2. This is nothing but inverse of response reduction factor. So if I reduce it to half, you can see that there is a permanent deformation. Then here I have designed it for 0.25, that means R is equal to 4, and so on. And as you are increasing the R, the permanent displacement goes on increasing. Okay. At the end of the earthquake, we get permanent displacement. And here it is shown that for what length or what duration the structure is in inelastic range. So you can see that the duration in which here there is no inelasticity, it was elastic only. Here it was in elastic range only during this time. So this duration in which the structure was in inelastic range, in inelastic response, that duration also goes on increasing as we design it for lower and lower yield force.
Sir,
That's all. Yes.
and sir, it is giving displacement only in one direction.
This is
Giving displacement only in one direction.
This is a single degree freedom system. The single degree freedom system, there is mass, and this mass is vibrating in one direction, and I have applied ground motion also in one direction. In reality, there will be 3 ground motions, but I am considering only one component of the ground motion.
The displacement is only showing about the bottom, the origin.
Displacement is only,
Showing bottom of the origin. Is
I
it
couldn't get, bottom of the origin means?
like in the first case, the F1R is equal to 1. It is giving the displacement in both directions.
Right. This is also giving in both directions. Here, because there is a permanent displacement has occurred. So what happened? Our single degree of freedom system, it deformed like this, and then there is a permanent displacement, and then it deforms at this location. So its mean position has changed. That's what we call permanent deformation. So it has undergone permanent deformation, and its mean position itself has changed. So elastic system will vibrate like this. In elastic system, initially it will vibrate like this, and then it will start vibrating like this. Then it may change, it may go other side, and it starts vibrating like that. So that's what you are seeing. So somewhere here, there was a strong pulse in this direction, and due to that, our structure, our single degree freedom system shifted permanently in that direction, and then it started vibrating. We can plot this response also on tripartite graph as we have done earlier. The response with period. Vertical axis is velocity. This axis is giving us acceleration. This axis is giving us the displacement. Okay. So here we can read all the 3 together. What I want to take to you is that if you look here, the ratio of elastic to inelastic response here, you see something interesting. These are for different values of Fi and for one earthquake. So you can see that beyond this t equal to 0.5 second, it is more or less 1. Okay, for one earthquake, it is zigzag because it is for one earthquake. If you will consider a number of earthquakes and then take average, you will get a smooth line corresponding to 1. What does that mean? That irrespective of the response reduction factor, the displacement is same in this period, means equal displacement principle. Whereas here you see, here what is happening? The lowest displacement is, or as the Fy bar is decreasing or response reduction factor is increasing, you can see that the displacement goes on increasing. So displacement of the inelastic structure is more than that of the elastic structure, and the displacement increases at the level of inelasticity. So for larger inelasticity, there is larger displacement. Whereas here in the long period range, it is more or less constant. Same observation we have used in our first semester as principle of equal displacement and principle of equal energy. Okay, so this is indicating if you do it for large number of earthquakes, then it will become smooth. Okay, and this will follow this line. Okay, now here something interesting has been done. So these are plotted for different values of ductility. Okay, Ry, different ratio. So different ratio means ratio of Fy to Fy. Okay, that is same as this R. So different values of Ry is equal to 1 is this. Ry is equal to 2, Ry is equal to 4, Ry is equal to 8. So Ry is equal to 8 means 0.125 Fy. So Fy bar is 0.125 Fy. And here this is ductility demand. Ductility demand is inelastic displacement to yield displacement. So you can understand that when you have used higher value of R, the ductility demand will be more. But this ductility demand you see is changing. It does not remain constant. Okay. Here also you see the ductility demand does not remain constant. Ductility demand changes with period. For one period of the structure, the ductility demand may be more. For another period of the structure, the ductility demand may be less. So it is varying in a zigzag manner. Okay. So what we are doing, we are taking a single degree freedom system. First we are analyzing it elastically. We will get the force. Now we will go on reducing that force by a fraction. First we made that force half, and then we performed its analysis. We calculated how much ductility demand is coming, maximum ductility demand. Then I reduced it to 1/4. Again I calculated the ductility demand. That I have plotted here, corresponding to different single degree freedom systems of different periods.
Sure. This Ry equal to 8, 4, 2. These are the ratios of the force, field force upon the design.
Strength.
Strengths.
Right.
But the ductility we calculate based on the displacement or propagation.
Right.
Theta u upon theta.
Right.
So how these are related?
These are not related. This I have computed. I have not quoted any relationship between them. What I have done is simply I have considered a number of single degree freedom systems. Earlier we have considered single degree freedom systems of different period. Let us say I have not considered different period. Period is same. But this is designed for, let us say, My. This is designed only for My by 2. This is designed for My by 4. This is designed for My by 6. And this is designed for My by 8. Okay. And I subject all of them to same earthquake. Then I will calculate mu here. 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 The ductility demand when it is yielding and when it is having the maximum displacement. So that ductility demand I will calculate for the same period, same damping, period and damping is same in all. But the capacity which I am providing here, that is different. So naturally this will yield, this will not yield, this will yield before this will yield before this will yield before this. So the ductility is going to increase, the ductility demand is going to increase. Okay, but this increase is not linear. That's what I want to show. Actually, there appears to be no relationship. This plot only shows, you were saying that how these can be related. Actually, these plots are showing that actually there appears to be no relationship. Only thing we can see is that for Ry is equal to A, it is more than Ry is equal to 4. And that is more than Ry is equal to 2. That we can say. But there does not appear to be a monotonic curve, a relationship, parabola or a straight line or anything. We can't fit that. Okay. So what we are trying to obtain is the.
So, sir,
Yes.
each point on the graph is representing corresponding to one time phase. T1, T2.
Each plot is representing
Each point on the
is
graph.
representing one period.
One period.
That means one such series which I have shown at T, one such series. So I have taken it from my Chopra, I have not done it. So what they have done there is that they have analyzed a large number of single degree freedom systems of one period and different Fy. Then another period and different Fy. Then another period and different Fy. Ground motion is same. So for same ground motion, when you are changing Fy, the ductility demand is changing like this. Okay, let's do reverse of this. I want to calculate, because finally I have to design ductility capacity is known in a structure. I want to design my structure for given ductility capacity. From here I am getting the ductility demand corresponding to value of Fy. Suppose I fix the value of ductility demand and I want to calculate Fy corresponding to that. So Fy corresponding to a ductility, given ductility demand of 2, ductility demand of 4, ductility demand of 6, depending on whatever is the capacity. I want to calculate corresponding value of Fy. How I will calculate? For that, I have to do iteration. Suppose period is 0.5 seconds and I have decided that I want a ductility demand of, let us say, 5. How will I obtain? Ductility demand of 5 here. This ductility demand I have a plot for Ry is equal to 2, Ry is equal to 4, Ry is equal to 8. I want to calculate Ry corresponding to this. How I will calculate? I have to do iteration. So I will consider a single degree freedom system of period 0.5 seconds and then I will design it for different values of My. And with each value of My, when I have done this as Ry is equal to 8, I will get this demand. When I have taken Ry is equal to 4, I will get this demand. So I know somewhere in between I will get. So I will perform another analysis with, let us say, Ry is equal to 5 or 6 or 7 and see when it is I am getting this demand. So I have to perform an iterative solution. And what that iterative solution is going to give me? Yes. Fy by W. What is that? Yield spectral acceleration. Okay. So yield spectral acceleration in units of G for given ductility. So mu equal to 1, that means elastic. So for elastic it will be nothing but the elastic response spectrum. Isn't it? In case of mu is equal to 1, this is nothing but the elastic response spectrum for this particular object. Then same I can do with any value of mu. I can plot the whole response spectrum. But obtaining each point here, I have to perform a number of iterations. When we do it for number of earthquakes, we get something very interesting. They have done this in tripartite, they have plotted. I want to skip this. I just want you to not give it this. Finally, we get something very interesting. Smooth shape. Like we have plotted response spectra for different value of damping, in the same manner we can plot response spectra for different value of mu deflected. Okay, so mu equal to 1 is actually same as we have used in code or site specific we have obtained. So that is mu equal to 1. For mu equal to 1.5, 2, 4, 6, 8. As the ductility capacity will go on increasing, the yield response spectrum will go on increasing. You have to keep in mind this is different than SA. This is SAY, at which it is yielding. Okay, not what the earthquake will cause on elastic structure. This is what we have to design our structure such that the ductility demand we will get is 2. So if I want to design my structure in such a way that the ductility demand should be equal to 2, then I have to design it for this value of yield force. I have to simply read from here. Suppose my structure is having a period of 1.5 seconds. So I have to, and ductility of 2. Then I will read the value of SAY from here. And I have to design my structure for Vy is equal to simply this SAY into the whole. How it is different from the original one? Original response spectrum? There we were getting Vb base shear SA into W. What was that base shear? That was the base shear which will occur if the structure is not yielding at all. Here we are obtaining this Vy when my structure will yield, and it will yield in such a way that the ductility demand under this earthquake will be equal to 2. So why we are doing all this? I know how much ductility is there in my structure. Once I know the ductility from this graph, I am knowing this period, and this period is TE. Okay, elastic period, not the secant period. This also you have to keep in mind. So if I know the initial period of my structure, I know how much ductility capacity it has, I can simply read SAY from here, and then I can design. I can calculate the yield stress, yield base shear for which I have to design. Okay. If I have to design for Vy, I have to consider the expected strength and partial factors of safety equal to 1. This is important because we are designing for Vy. Normally what we are doing, we are designing for Vb. Okay, so that will be Vy divided by overstrength. You know, we have done this relationship earlier also. SA versus SD or VB versus delta also we can plot. This is VBY and this is VBD, and this ratio is only. And from where we are getting this ratio? Why VBY is higher than VBD?
Because we want structural.
Because
we want structural industry.
why it is higher? You are designed for VBD, but you are getting VBY. Why? I have told this earlier also. Same thing I am asking you, not new. Because of two reasons: characteristic strength and partial factors. So that is giving rise to this. So same thing is applicable here. If you have to design your building using limit state method, what you have to do from this method? First, from that period, for that period and the ductility, you will get SAY. Then you will calculate BBY as SAY into W. And then you will calculate BBD as BBY over W. And then you can design using our normal limit state. This spectrum is called constant ductility spectrum or yield spectrum. So a different way of representing earthquake ground motion. What is response spectrum doing? Response spectrum is representing earthquake ground motion, demand. So the same demand is represented in a different fashion here. And this demand takes into account the ductility capacity available in the structure or the ductility capacity which you want to utilize. Suppose the total ductility capacity is 4, ultimate, where the failure will occur, collapse will occur. You don't want to utilize 4, you want to utilize only 2. So you can take it like this. If you want to utilize 4 in the same structure, then you can see that this is going to reduce. You will design for now. Reduce force. So if you decide that I don't want to have that much damage, I want to have a smaller, lower damage in my structure. So in that case, you can reduce the value of ductility to 1, which you want, and accordingly you can design your structure.
Sir, for getting ductility equal to 2 or what of the so first I have to design my building, providing reinforcement and all. Then I have to provide now that I will make ductility equal to 2. Now that ductility equal to 2, I will make BBY. That means for that ductility, this much square boxes are about structure.
This much force I should design.
I should do, no, I have designed ductility. That's why I am getting a value of 5.
You have designed, but that design is may not give you the desired value of mu.
No, desired value. Let's say I have taken this, I provided a function, provided a fiber, and from that fiber I am getting BBY by making plastic in this function for all these things. It means what whenever I apply BBY force on this element, then element is going to the lead and that much force is taken by the same element. If I am applying earthquake motion on this structure and I am getting the demand like if that ratio is less than this BBY, then I say the structure is safe now. Until there is a comment, what of them is going to be. Then what is the use of this?
Suppose that comes out to be less than this.
Then I
That
will
is what you have originally designed is less than this.
then I will increase my ductility.
Not in ductility you can't increase. Can you increase ductility of a structure? How will you increase the ductility of a structure?
Means I will again modify my design requirements in that element.
How?
By providing that.
Can you suppose I want to design a member with ductility equal to 60. Can I design? No. So ductility depends on the detailing. So that is more or less fixed. You can't do too much with ductility. Little changes you can make in ductility by avoiding some of the failure modes. Okay, for example, if shear failure is occurring, then ductility will be less. You can increase that. But maximum ductility what you can achieve, there is a limit. You can't increase beyond that. So what you have to do? You have to design your structure for higher base shear. So what should be that base shear which you should design for minimum? That is there. If you have already designed for larger than this, fine, you should be happy. Or you can even reduce that because that much is not needed.
But sir, when the ductility is fixed, it means capacity is also fixed.
How? If ductility is fixed, capacity will also depend upon this responsive spectrum, and responsive spectrum will vary from side to side. Ductility is different, so strength has two capacities. Sorry, the structure has two capacities. One is the strength capacity, another is the ductility capacity. Ductility capacity is more or less fixed. You can't do much with that. But strength is in your hand. You can achieve any strength. You design it for larger sizes and reinforcement. The strength can increase. So you can control strength, but ductility you can't control that much. Some control on ductility is possible because if you follow ductile detailing, the ductility is going to increase. If you follow capacity design, the ductility is going to increase, but there is a limit. You can't go on increasing this in an unlimited manner. But strength you can go on increasing in unlimited manner. You can design for any ratio.
Sir, you are saying that if this is the capacity curve,
Yeah.
VY versus delta, this delta I can't increase for
Yes.
particular member. But
Right.
I can reduce this force here. I will design for this force, and the maximum force that is yield force that member can take is this much VBY.
No.
And I will design for this force.
No. Let me explain you the way you are thinking. It may be building, it may be a structure. You are applying a force and you are plotting force versus delta. So this plastic deformation will remain more or less constant. You can't change it. But what you can do is, you can change this strength. So you can go on increasing the strength, and stiffness also changes. When you are changing the strength, actually you are increasing the member size. You are increasing the reinforcement. So actually, I have not taught you this, but I will teach you later. This delta y remains same. Delta y does not change. Delta u also does not change, but Fy can change. You can change Fy. How? By putting larger this column size. One case it is this, another case you take this size, put more reinforcement into it. So you can go on changing its Fy, the force at which it is yielding. Okay. When you are changing the size and the reinforcement, actually stiffness is also changing. Stiffness is also proportional to strength. It depends on strength.
So if the stiffness is increasing, it will attract more force from earthquake motion.
From the response spectrum.
Response
Yes.
spectrum. Then again force is coming large, and I am increasing strength also. So there will be
The increase in force will not be that much as the increase in the strength. Okay. So even if stiffness and strength are proportional, the period is proportional to 1 upon root k, and SA is proportional to 1 upon T. So the demand will increase square root times, and the capacity will increase by proportional. Okay. So increase in demand will not be that much as the increase in the strength. But you are right. If I am making the structure stiffer like this, then when I am increasing the strength, actually I am increasing the demand also, because of the shape of our response. Okay. So using this, there is another possible method of performance point evaluation. Actually, this spectrum or constant ductility spectrum or yield spectrum, you can draw very easily. You need not to perform so many analysis. I have told you that you have to perform analysis, then at each period you have to do iterations for different values of Fy so that you get the targeted ductility. All that is not needed. You can do it very easily. People have already done that and seen it, remembering these 3 points. So this Ry is the ratio of the elastic spectrum to the yield spectrum for any value of mu. Okay. So Tn less than Ta, What is TA? 33, 1 upon 33 seconds. So there it is 1. That means all the yield spectra are starting from here. So TA is this small point. So this will remain same. During this, in this period range, the value is same. The starting point is same. Then there is one reduction factor here, another reduction factor here. So in the acceleration control range, the reduction factor is square root 2 mu minus 1, and in the displacement control range it is mu. So for any value of mu, you can plot this response spectrum very easily. Can you do it or not? Here it will be reduced by square root 2 mu minus 1. Here it will be reduced mu times intersection of those two will give you this speed. So you can plot the yield spectrum for any value of mu. Now knowing this yield spectrum, how to get performance point? Same way as we have done in ATC 40, we will use iterations, but those iterations will be done slightly different. We have got the capacity curve. Capacity curve we have converted into equivalent bilinear curve. This is SDY, okay, and the demand curve. Demand response spectrum is here. Now, let us say this is my target spectral displacement SDO. I can calculate the ductility demand here. mu1 as SD1 over SDY. Can I do that? The displacement I can calculate. Elastic displacement will be this. So I will assume this SD and SD1 very close. Okay, close to it. I will do that. I know the mu. Now for this mu, I can reduce. I can calculate Ry and I can reduce this response spectrum like this. And then I will calculate the displacement now corresponding to this reduced spectrum. And that displacement, if it comes out to be close to this, okay, so you have to keep in mind that this is reduced by Ry, but the period is initial period only. Okay, so you have to calculate displacement corresponding to initial period only. So the mu SD will be equal to SA over Ry into TE square divided by 4. Let me call this SD2. If SD2 is close to SD1, then the solution is done. So what is the difference compared to ATC 40 method? That in place of damping, we are using ductility for reducing the noise. And here, the displacement was calculated at the secant period. Here we are not calculating at secant period. Here we are calculating at CE, initial or elastic. That's the difference. Otherwise, the iterations will remain same. And reduction here is very simple. Value of Ry is very simple. It is square root 2 mu minus 1 in the acceleration control range, and it is equal to mu in the velocity and displacement. Okay. This is also called Newmark's method. Newmark developed this value of Ry, considering large number of earthquakes, and from here only this equal displacement principle and equality principle has been developed, which we have used in our first semester. So that covers your tutorial number 5. We will have one class for discussion tomorrow. So tomorrow we can discuss tutorial number 5, and tomorrow you will also tell me the day, if any, you want to comment.